In the last module, we looked at simple linear regression as a technique for fitting models that consist of a linear relationship, one that can be represented as a line on a graph. In this module, we will extend this technique in three distinct ways. First, we will look at a situation where the relationship between two variables is described not as a line, but as a polynomial. Second, we will look at cases where more than one explanatory variable is employed by the model. And finally, we will look at classifying a response variable when that variable is categorical rather than continuous, using logistic regression. Along the way, we will develop a statistic for assessing model performance. Upon completing this module, you should be able to, first, understand the basic principles of polynomial regression and when it is applicable. Second, understand the basic principles of multiple linear regression and when it is applicable. Third, be able to understand the basic principles of logistic regression and when it is applicable. And finally, you should be familiar with the calculation and interpretation of a simple metric, the R-squared metric, for measuring model performance. First, let's look at models containing a relationship between a single explanatory variable and a response variable that is described by a more complex relationship than just a line. What are some examples of such a relationship? Here's one example. If we plot global human population, the response variable, as a function of time, the explanatory variable, we see that the data clearly does not follow a line, and trying to fit a line to this data will lead to poor model performance. Here's another example, bacterial growth rate as a function of temperature. Again, this relationship is nonlinear, and trying to fit a simple line to this data would lead to a very poor model. We need some better techniques to address relationships such as these. Let's look at the case of a relationship between a single explanatory variable and a response variable. Further, let's suppose that this relationship can be captured by a polynomial. A polynomial is a relationship consisting of linear combinations of coefficients and various powers of the variables. A first-order polynomial consists of terms up to x to the first power. A second-order polynomial contains values of x raised to the second power, and so on. Taking an approach similar to what we did with the simple linear regression, we can estimate error in a polynomial model by summing the square of the difference between our observations and our model over all observations. Continuing the approach we use in simple linear regression, we differentiate our error function with respect to each model parameter, generating the normal equations. And because we are looking for a minimum of the error function, we set these derivatives to 0 and solve for each model parameter. I'm not too concerned if you don't follow all the details of the math at this point, but you should be able to follow the general concepts of regression and see how they are manifested in the math. The solution is slightly more complicated than in the case of simple linear regression, but a direct solution is still possible. Because this is a system of m+1 linear equations with m+1 unknowns, it is easily solved with a technique like Gaussian elimination to get the best fit parameter values. A useful question to ask is, how good is the model at fitting the data? As we have seen, in most cases there is some difference between a model prediction and an observation. That difference represents model error. We have also seen that for a given set of model parameters, we can quantify that error by summing the square of the difference for each observed point and the model, resulting in the error sum of squares. We can normalize the error sum of squares by dividing the number of observations adjusted for the number of parameters in the model and taking a square root to generate what is termed the standard error of the estimate. The standard error of the estimate roughly represents an average error per observation in units of the observation. We adjust the denominator by the number of parameters to account for the fact that more parameters provide more degrees of freedom to fit a given data set. Models with many parameters can often provide a good fit to the data for no other reason than the flexibility large numbers of parameters provides in contorting the model to fit a data set. and may not reflect reality well. An additional useful metric of model performance is a goodness of fit statistic measuring how much of the variability observed in the data can be explained by the model. Ideally, a given model will explain all of the variability in an observational dataset, meaning it would perfectly predict all data points. Conversely, a poor model would explain very little or none of the observed data. To get at this, we look at two cases: the sum of the square around the mean of the data, and the error sum of squares that we have seen before. The sum of squares around the mean can be thought of as the error sum of squares associated with a model that doesn't consider the explanatory variable at all. This model is termed the null model. A difference between the two statistics is a measure of the improvement in the model prediction of the full model compared to the null model. We can normalize this statistic by dividing by the sum of the squares around the mean to generate a unitless measure of error that captures the percent of the variability of the observed data explained by the model. This is termed the R-squared value, also called the coefficient of determination. A perfect fit between model and observations results in an R-square of 1. In contrast, if the model provides no improvement in the predictive capacity compared to the null model, then the R-squared will be 0. For most problems you are likely to encounter in ecological engineering, reasonable R-squared values generally run between about 0.5 and 0.9, meaning these models typically can explain about 50 to 90% of the variability in an observed dataset. Next, let's look at models that are still linear but have more than one explanatory variable. For example, the yield of a particular crop may be a function of both the amount of applied water and the amount of applied fertilizer. As long as these explanatory variables are present only as linear combinations in our models, we can take a similar approach to what we have done with simple linear regression and polynomial regression. As before, we calculate an error sum of squares by summing the square of the differences between our observations and our model predictions for those observations, then differentiating the result with respect to each model parameter and setting the results to 0 to generate the normal equations. Here we show what this would look like for a model with two explanatory variables. As before, if you don't follow all the details of the math, that's okay, but you should be able to follow the general concepts expressed in the math. In this case, our multiple linear regression result is a system of 3 linear equations with 3 unknowns and 3 model parameters that we can easily solve using Gaussian eliminations or a similar technique for solving systems of linear equations. This technique is easily extended to more than 2 explanatory variables. We won't go into all the details here, but it follows the same approach we have developed previously. Another form of regression that is commonly used is logistic regression. While not technically a form of linear regression, logistic regression is conceptually similar to linear regression, but is used in cases where the response variable is categorical rather than continuous. Examples of categorical response variables include binary variables like species presence or absence, or whether you are likely to pass or fail an exam, examples where there are only 2 possible outcomes, or multi-valued variables that are still categorical but may be one of 3 or more distinct values. The former case, with 2 categorical variables, is referred to as binary logistic regression. The latter case is referred to as multiple logistic regression. In any case, it is useful to think of logistic regression as a classification process predicting the probability that a given response class is indicated by the explanatory variable. The basic idea of logistic regression is to estimate the probability or likelihood of observing a particular response variable value, also referred to as a class. Logistic regression assumes that the log of the probability of observing the class divided by the probability of not observing the class is a linear function of the explanatory variable. This ratio is generally referred to as the odds of observing the class. In this case, the model parameters A0 and A1 can be estimated by transforming and rearranging the logistic function to solve for the probability of observing the class, where these probabilities are taken from individual observations. Logistic regression is similar conceptually to linear regression, but because of the log transform, this is technically a form of nonlinear regression and requires a somewhat more sophisticated solution method as a result. We can't directly calculate the best fit values and must instead apply an iterative solution technique. We will be covering nonlinear regression in a subsequent module. So, to recap this module, we saw that we can easily extend the general approach we saw previously for simple linear regression for additional functional relationships as long as the error function is linear with respect to each parameter. In the case of a single explanatory variable where the model relationship is polynomial, we could apply polynomial regression to find the best fit parameters for a given observational data set. In the case of multiple explanatory variables, where the model relationship consists of a linear combination of those explanatory variables, we would apply multiple linear regression to find the best fit parameters for a given observational data set. We also looked at logistic regression used when our response variable is categorical and we are trying to estimate the probability of observing a particular class for a given level of an explanatory variable. Just as with linear regression techniques that we have used so far, logistic regression relies on having an observational data set to estimate best fit parameters for the model. Finally, we developed a goodness of fit statistic for measuring model performance, specifically how much of the variability of the observed data our model explains when compared to the null model not containing the explanatory variable.